Welcome to the high-speed data connectivity presentation. My name is Michael Hennerich. I'm Engineering Manager in Munich, Germany. Today we want to talk about high-speed converter interface styles and standards. Then we take a closer look at the JESD204B Converter-to-FPGA serial interface. After that, I'd like to introduce our FPGA converter systems design support offerings. High-speed data converter may only attach to FPGA in ASICs. To counteract increased development cost and to simplify development, ADI provides a number of design support offerings helping customers to reduce risk and accelerate development of high-speed converter systems. Now take a closer look at some typical high-speed converter output configurations. The numbers provided here are just some thumb rules for ADCs and may vary based on capacitive loads, trace lengths, etc. We start with source synchronous parallel output configurations. CMOS tops out at around 150 megasamples, while LVDS goes up to 500 megasamples and much more. Low voltage differential signaling uses a pair of complementary outputs, thus twice the pin count for the same number of bits as in CMOS. But with the double data rate interface typically used, the number of traces, pins, is on par with CMOS implementations. Parallel interfaces are high pin count, typically converter resolution plus clocks and some framing signals. But the interfaces are available in the lowest cost FPGAs. Serial LVDS is technically similar to parallel LVDS. It's used when pin count is a priority over interface speed. The maximum interface rate is greater than 1 gigabits per second. The max data rate is a function of resolution and number of lanes. The number of traces pins is the number of lanes plus clock and frame. JESD204 uses current mode logic and uses 2 pins per lane. The number of lanes depend on the number of channels, speed and resolution. In order to interface with JESD204 converters, gigabit transceivers are required, which are only available on higher-end FPGAs such as Virtex or Kintex FPGAs. More details on JESD will follow on the coming slides. Besides the data interface, converters typically also feature a control interface. Most often it's a 3 or 4-wire SPI interface with speeds below 40 MHz. Sometimes also I2C is seen. This control interface is used to access the on-chip configuration registers and requires dedicated software device drivers to set up and control the converter. Low-speed precision converters may combine data and control using an SPI or I2C interface, or some converters are pin programmable or may not have a control interface at all. So why the need for a high-speed converter to FPGA serial interface? Let's look at a typical MIMO, multiple input, multiple output example. Today's solution is a challenge for PCB design. In this example, there are more than 100 wires. Transmission lines need to have controlled impedance and match source and sink. Lengths of transmission lines used for differential traces need to be approximately the same. If not matched, the link can become unreliable. In such MIMO systems, this queue between 2 or more converter devices, called inter-device queue, is also relevant. The same solution with the JESD204 serial interface may look like this. In this case, there are around 23 wires, which require a minimum number of I/O and are easier to route. There are provisions within the standard easing timing requirements and all kind of system queues. There are 2 obvious ways to add bandwidth. Either increase the bus speed or add parallel channels. Prior to the advent of high-speed interface, the later approach was often chosen, resulting in wide buses with all their implications when it comes to system design. To simplify system design and further scale bandwidth requirements, a new approach is taken by using high-speed serial interface. So, what are the benefits? It's simplification of the overall system design. Lower number of trace routes allow easier routing of board designs. Synchronization also becomes easier. It's reduction in pin count on both the transmitter and the receiver side. Move from high pin count, low speed parallel interfaces to low pin count, high speed serial interfaces. Embedded clock and framing even further reduce the total pin count. It's also a reduction in system costs. Smaller IC packages and board designs led to lower cost. It's also easily scalable to meet future bandwidth requirements. As geometries shrink and speed increases, the standard adapts. What drives all this is dollars, watts, and square millimeters of board space. SerDes, short for serialize deserialize, is sometimes used instead of JEST-204. SerDes is simply a generic name for any serial interface. JEST-204 is a JEDEC-defined standard for high-speed, multi-gigabit point-to-point serial interface used to interconnect two or possibly more devices. How is it different than previous data converter interfaces? A single primary serial interface is used to pass all data, clocking, and framing information. The clock and frame information are embedded in the data stream. There's no need to worry about the setup and hold times between data and clock anymore. One differential PCB trace can route all bits. Let's talk a little bit about the history of the JEST-204B standard. In April of 2006, the original version of JEST-204 was released. The 204 standard describes a multi-gigabit serial data link between converters and receiver, commonly a device such as an FPGA or ASIC. In this original version of JEST-204, the serial link was defined for a single lane between a converter or multiple converters and a receiver. The lane is a physical interface between m number of converters and the receiver, which consists of a differential pair of interconnect utilizing current mode logic, drivers and receivers. The standard needed to be revised to incorporate support for multiple aligned serial lanes with multiple converters to accommodate increased speeds and resolutions of converters. This realization led to the first revision of the JEST-204 standard in April 2008, which became known as JEST-204A. This revision of the standard added the ability to support multiple aligned serial lanes with multiple converters. The lane data rate of up to 3.125 gigabits remained unchanged. Although both the original JEST-204 standard and the revised JEST-204A standard were higher performance than legacy devices, they were still lacking a key element. This missing element was deterministic latency in the serialized data on the link. When dealing with a converter, it's important to know the timing relationship between the sampled signal and its digital representation. So in 2011, the second current revision of the JEST-204B standard was released. One of the key components of the revised standard was the addition of provisions to achieve deterministic latency. In addition, the data rates supported were pushed up to 12.5 gigabits per second. This revision of the standard calls for the transition from using the frame clock as the main clock source to using the device clock as the main clock source. The figure shown gives a representation of the additional capabilities added by the JEST-204B revision. Let's now take a look at some key aspects of the JEST-204 standards. An 8B, 10B embedded clock is utilized, which uses DC balanced encoding. This guarantees significant transition frequency for use with clock and data recovery techniques. This encoding allows both data and controls characters to be used. The control characters can be used in specifying link alignment, maintenance, monitoring, etc. This encoding also allows for the detection of single bit errors that may occur on the link. Serial lane alignment is achieved by using special training patterns with control characters that allow lanes to be aligned across a link. This allows for the trace-to-trace tolerance to be relaxed in comparison to synchronous parallel LVDS designs. Serial lane maintenance is accomplished through superframe structure and by using specific characters to guarantee alignment. The link quality is monitored by the receiver and is done on a lane-by-lane basis. It's important to note that the link is established and dropped by the receiver based on error thresholds defined within the JST204 specification. Let's move on now to discuss some key signals in JST204A systems, as this is the most prevalent version in use. The frame clock in JST204A is a clock signal used in the system that is equal to the frame rate of the data on the link. The frame clock serves as the master timing reference. The sync bar signal is a system synchronous active low signal that goes from the receiver to the transmitters and denotes the state of synchronization. This signal is synchronous to the frame clock in JST204A. When the signal is low, it implies the receiver and transmitter are synchronizing. The sync bar and frame clock should have similar compliance to ensure proper capture and transmission timing. For example, LVDS, CMOS or CML could be used as long as both sync bar and frame clock utilize the same signal type. Lanes are defined from lane 0 to lane L-1. These are the differential lanes that exist on the JST204A link. Due to the high speed of data transfer, these are typically high-speed CML. In a JST204B system, the sync bar signal is again present, but in this case the signal is synchronous to the local multi-frame clock, or LMFC, instead of the frame clock as in JST204A. Lanes are assigned just as they are in JST204A, from lane 0 to L-1. An optional signal called sysref is a source synchronous high slew rate timing resolution signal that can be used for resetting the device clock dividers, including the LMFC. This helps to ensure deterministic latency. It can be one-shot or periodic and is distributed to both ADCs, DACs and ASIC FPGA logic devices in the system. When available, the sysref signal is the master timing reference in JST204B, since it's responsible for resetting the LMFC references. I've mentioned deterministic latency a few times, so let's take a closer look to understand it a little bit better. So latency is defined as deterministic when the time from the input of the JST204 transmitter to the output of the JST204 receiver is consistently the same number of clock cycles. When you have a parallel implementation, deterministic latency is simple, since clocks are carried with the data. However, in serial implementation, multiple clock domains exist, which can cause non-determinism. The JST204 and JST204A specification contain no provisions for guaranteeing deterministic latency. In the B version of the specification, there are 3 subclasses of devices described, which address this idea of deterministic latency. The 3 subclasses are 0, no support, 1, deterministic latency using the sync bar, and 2, deterministic latency using the sysref signal. Let's now look at the physical signaling layer, in particular the logic drivers. JST204 uses current mode logic. If you compare these versus LVDS, you will see that they are similar. CML works up to 12.5 gigabit, however, it has higher power consumption compared to LVDS. The increased speed of CML driver leads to a reduction in the number of drivers by enabling more channels per lane. With JST204 providing up to 80% lane reduction, the power increase of JST204 CML is comparable to an LVDS implementation. Let's do a quick summary. High-speed converters only attach to FPGAs and ASICs. Converters typically feature control and data path. The data path requires FPGA HDL interface logic. High-speed serial interfaces tend to be more sophisticated and therefore require even more know-how and logic. Dedicated control interface, typically free 4-wire SPI. SPI interface can use standard IP cores provided free of charge by most FPGA vendors. However, often more than 100 registers with lots of control bits. The complexity is with the software and initialization values. To reduce customer risk and to speed up development and integration, engineers may benefit by good documentation, reference and development hardware, support and help, tested reference HDL code and software drivers. How can analog devices help you with that? Analog Devices provides reference designs and evaluation boards that directly connect to typical FPGA development platforms using industry standards. This allows engineers to start HDL software and application development on a known working and well-supported platform. In contrast to custom hardware, this approach simplifies support requests since issues can be more easily recreated on either the FPGA or converter vendor side. ADI provides tested and flexible HDL interface blocks and software device drivers, which can directly be used in the end system design. This frees up engineering time for standard components and allows us to better focus on value-added application development. ADI tries to provide good documentation for boards, reference designs, HDL and software deliverables. For customer support and interaction, there's the Engineer Zone and our community wiki. More on each of these points in the following slides. FPGA Mezzanine Card, or FMC, as defined in Vita 57, provides a specification describing an I/O mezzanine module with connection to an FPGA or other device with reconfigurable I/O capability. Analog Devices converter products can be found on many boards which use industry standard FMC connectors. To mention just a few, the FMC Imagion board is a 1080p HDMI transmitter and receiver solution. The 9467 FMC board is based on a AD9467, which is a 16-bit 250 megasample analog to digital converter. The 9739A FMC board is a 14-bit 2.5 gigasample high-performance RF DAC capable of synthesizing wideband signals from DC up to 3 GHz. The AD-FMCOMS1 EBSET is an analog front-end hardware platform that addresses a broad range of research, academic, and industrial and defense applications. The AD-FMCOMS1 EBSET enables RF applications from 400 MHz to 4 GHz. The AD9265 FMC board is based on the AD9265, which is a 16-bit 125 megasample analog to digital converter. The Analog Devices AD FMC JSD ADC1 EBSET is a high-speed data acquisition rapid development board providing 4 14-bit ADC channels at 250 megasamples in a FMC form factor. It contains two AD9250 dual analog to digital ICs, which support high-speed serial JSD204B coded outputs for improved FPGA connectivity. The board may be clocked by either an internal clock source or by an externally supplied sample clock. The card is mechanically and electronically compliant to the FMC standard ANSI Vita 57.1. There is an ADI Xilinx HDL reference design available, as well as device drivers for Linux and NoOS. Analog Devices provides evaluation boards for most of our converter products. These boards typically use an in-house standard called FIFO connector, incompatible with FPGA evaluation boards. Purpose of this adapter interposer board is to provide electrical and mechanical connection with an FMC HPC connector. If you are trying to evaluate analog converter performance, we encourage you to use the official evaluation board first. Native FMC cards such as the AD-FMC JSD ADC1 EBSET may not achieve 100% datasheet specification. SFDR, for example, may be off by half a dB due to the compact layout, missing shields, and simplified power management. Here we see the FMC-ADC Interposer at work. The official AD9250 EBSET evaluation board connected via the adapter to a Xilinx Kintex 7 KC705 FPGA development board. Everything told about the FMC-ADC adapter also applies to the FMC-DAC adapter. The AD-DAC-FMC-ADP adapter board allows any of Analog Devices DPG2 compatible high-speed DAC evaluation boards to be used on a Xilinx evaluation board with an FMC connector. The adapter board uses the low pin count version of the FMC connector, so it can be used on either LPC or HPC hosts. The FMC SDP Interposer allows any Analog Devices system demonstration platform evaluation boards or circuits from the lab reference boards to be used on a Xilinx evaluation board with an FMC connector. The Interposer uses the low pin count version of the FMC connector, so it can be used on either LPC or HPC hosts. Since there is no active logic level translation on the Interposer, it can only be used with FPGA boards that support 3.3 volt I/O on the FMC. ADI products can be found on many boards which use industry standard connectors such as Pmods and FMC. Pmods are small I/O interface boards that offer an ideal way to extend the capabilities of FPGA or CPLD boards. Pmods communicate with the system board using a 6 or 12 pin connector. Pmods include sensors, I/O, data acquisition, conversion, connectors, and many more. Check the Digilent or Avnet webpage to see all Pmods featuring Analog Devices converter products. Analog Devices provides HDL reference designs for native FMC converter cards, converter evaluation boards using the previously discussed FMC interposers, Pmods, SDP or circuit from the lab type cards. Each reference design consists of a complete FPGA design project, including HDL and Verilog IP cores for the various components. There is documentation on the Wiki. No OS drivers and setup and test code. No OS drivers are purely written in C and feature an hardware abstraction layer. Linux device drivers are also available where applicable. Source of all information is the Analog Devices Wiki. ADI provided HDL IP blocks typically provide following functions. They drive converter control signals in accordance with datasheet, interface and timing requirements. They sample data, abstract and mediates them up in the hierarchy. They take over converter typical pre- and post-processing tasks such as data and format conversions, applies scales and offsets or do sign extensions. In a multi-channel converter, they allow extracting or selecting parts of the data. Interface timing validation using test modes and pseudo-number checkers. They provide status and error tracking such as overrange, DMA status, overflow and underrun. Last but not least, they allow engineers to insert custom IP while maintaining the interfaces on both ends. This reference design provides the audio and video interface between the FPGA and our ADV7511 and ADV7611 HDMI transmitter and receivers. A frame buffer typically uses an RGB 888 color space, while the HDMI transmitter expects an 16-bit YZBZR444 stream. Functional blocks within this HDL IP core are a color space converter, converting RGB 888 into YZBZR444, a color space subsampler, converting YZBZR444 into YZBZR422, a framer that is adding the embedded syncs. For the audio interface, we implemented the generic single-bit SPDIF interface, allowing audio in both directions. This whole design utilizes a minimum number of FPGA I/Os. Our HDMI transmitter solution can be found on various Xilinx evaluation boards: ZC702, ZC706, Z-board, KC705, and these are just a few to mention. We also provide Linux device drivers for the Direct Rendering Manager or DevFB and video for Linux too. For audio we leverage the ALSA system-on-chip framework. This slide illustrates the HDL blocks used in the FMC-ADC ADC1 reference design, which includes the Xilinx Logic Core IP JST204 core. Logic blocks include the ADC and DMA interface, including pseudonumber monitors for data integrity validation, and enhanced standalone iSCAN state machine interfacing with the GTX gigabit transceivers. This reference design is available for Vertex 7, Kintex 7, and also some other platforms. Now first take a step back. At high line rates, the receiver eye measured on the printed circuit board can appear to be completely closed even through the internal eye after the receiver equalization is open. As lane rates and channel attenuation increases, receiver equalizers are often enabled to overcome channel attenuation. Equalization techniques work at the receive end while pre-emphasis on the transmitter, by selectively boosting the high-frequency components in order to compensate the channel's high-frequency roll-off. This poses a challenge to system bring-up because the quality of the lane cannot be determined by measuring the far-end eye opening at the receiver pins. In addition, real-time oscilloscopes for multi-gigabit CRDES measurements cost more than some people, houses, or cars. So, how can we reliably determine the link quality? The RX iSCAN in Xilinx GTH, GTX, and GTP transceivers of the 7 series FPGA provides a mechanism to measure and visualize the receiver eye margin of the equalizer. Statistical iSCAN functionality on per lane basis is based on a comparison between the data sample in the nominal center of the eye and the offset sample captured by an independent and identical circuitry at a programmable horizontal and vertical offset. Bit error is defined as a mismatch between these two samples. Taking bit error measurements at all horizontal and vertical offsets allows drawing a 2D eye diagram while enabling bit error measurements with high confidence down to 10 to the power of minus 16 or 17. This slide summarizes the iSCAN example. This whole demo setup runs the analog devices reference design, which includes the Xilinx Logic Core IP JST204 core, and streams converter samples over Ethernet to visual analog, where the data can be examined with a powerful analysis tool with a user-friendly graphical interface. In addition, we visualize the data also on a Linux graphical desktop system that runs on the Sync FPGA ARM Cortex A9 processing system, while concurrently solving the most challenging hardware design verification task by measuring and visualizing the receiver eye margin on all JST204B lanes. Analog Devices provides no OS device drivers for most of our reference designs. However, in the next few slides, I'll focus on the OS Linux device drivers. I'll start by explaining why Linux is such an ideal operating system and what the advantages are. So Linux is widely used as an open source desktop server and embedded OS. It's very feature rich. It supports symmetric multiprocessing, preemptive multitasking. It has excellent real-time performance, supports shared libraries, it supports countless device drivers, state-of-the-art memory management. There's support for almost any networking and protocol stack or file system available. Last but not least, Linux kernel is free and open source software, licensed under the GNU General Public License and therefore easy to extend and modify. Linux is an ideal operating system and a significant part of the ecosystem for FPGA hard and soft cores. It runs on almost any common FPGA soft or hard core. I'll mention the most popular ones here as some examples. The main advantage of both hard and soft core is that we can eliminate external coprocessors, plus having a much faster and more closely coupled data route between the fabric and the core. The pros of hard cores compared to soft cores is the increased speed and fewer power consumption and gate usage. Let's start with some Linux driver model basics. The Linux driver model breaks all things down into buses, devices and classes. A bus can be described as something with devices connected to it. A device class describes common type of devices, like sound, network or input devices, sometimes also referred as Linux subsystems. Each device class defines a set of semantics and programming interface that devices of that class adhere to. Device drivers are typically the implementation of that programming interface for a particular device on a particular bus. Device classes are agnostic with respect to what bus a device resides on. The unified bus model includes a set of common attributes which all buses carry, and a set of common callbacks such as ideal device discovery during mandatory bus probing, bus shutdown or bus power management, etc. Device drivers are agnostic with respect to what processor platform they run on, in case they are registered with a common bus that the target platform supports. This ultimately means that, for example, a SPI converter driver for a specific part runs on any system with a SPI interface controller without any modifications to the driver source. The Linux Industrial I/O subsystem is intended to provide support for devices that in some sense are analog to digital or digital to analog converters. Devices that fall into that category are ADCs, DACs, accelerometers, gyros, IMUs, capacitance to digital converters, pressure, temperature or light sensors. I/O can be used on ADCs ranging from SoC ADC to more than 100 megasamples industrial ADCs. The Industrial I/O subsystem mostly focuses on user space abstraction, but also an in-kernel API for other drivers exist. For example, the I/O to Linux input or hardware monitoring subsystem bridge. In Linux, like in any other operating system, there is a separation between user space, application code, and kernel OS code. Applications run all in a private memory space and therefore are not allowed to call kernel functions directly. All interaction are done through system calls and the virtual file system. This block diagram shows where the I/O subsystem is located, how it interacts with the underlying device drivers, buses, drivers, and finally the hardware. Each and every I/O device, typically a hardware chip, has a device folder under sysbus I/O devices I/O device X, where X is the I/O index of the device. Under every of these directory folders resides a set of files, depending on the characteristics and features of the hardware device in question. These files are consistently generalized and documented in the I/O ABI documentation. In order to determine which I/O device corresponds to which hardware device, the user can read the name file. In the screenshot shown, we see some typical attribute files for a 2-channel ADC. In Linux, everything is a file. I/O control happens via sysfs, a virtual file system, virtual in the sense of there's no physical file on storage. Reading the file will call back into the device driver, which then feeds the content. There's I/O data via device nodes for large data buffer reads and writes. These device nodes can be found in the dev folder. Sysfs attribute files may control converter modes, are used to enable disable channels, are used to query data format, byte order, alignment, or the index, query and set sampling frequency, test modes, reference levels, and many more. A basic user space application code snippet is shown. It's basically open file path, get a file descriptor, then use read and write C library calls, and finally close it. Here we see an example device driver for a variable gain amplifier. Besides the name attribute, there's also the out voltage 01 hardware gain attribute, which allows to individually set the gain in dB for each amplifier in the package. This can be done from the command line interface via shell script from program code or over the network. This interface is human readable and very convenient and powerful. This example shows the AD9517 multi-output clock generator with distribution control found on the FMC-ADC ADC1 board. The device driver allows you to set and get frequencies in Hertz and or enable or disable specific output channels. Besides the user interface, it also implements an kernel interface, allowing other device drivers to utilize the same functionality the driver exports. Here is another example from the FMC-ADC ADC1 reference design. This device driver controls the JST204B receiver interface HDL IP. It provides easy of use RX iScan without any runtime overhead, direct read access to the JST204 link parameters, which are exchanged during the initial lane alignment sequence. This is particularly useful for debug and monitoring purposes during and after hardware bring-up. The JST204B receiver interface HDL IP customization and configuration happens via device tree. It's basically a human-readable file that describes the buses and the devices that may appear. It's heavily used with buses and devices that are not hardware discoverable. This screenshot shows the graphical front-end GUI of the JST204B receiver interface Linux device driver. The analog device's 2D statistical iScan application runs natively on a synced ZC706 development board. It allows you to select the lanes that you are planning to take iScans and set the bit error scan depth. Once started, it will then capture the lanes with the requested depths. They are visualized and the eye opening is calculated. Depending on the scan depth, one lane capture will take less than 22 seconds or it will scan for several days. Visual Analog is a software package that combines a powerful set of simulation, product evaluation, and data analysis tools with a user-friendly graphical interface. It can be used to measure and visualize SNR, SFDR, total harmonic distortion, power, and many more. The I/O command client is a new feature and will allow you to control the Linux I/O device drivers and capture data via TCP network connection. This wiki provides developers using analog devices products with software and documentation, HDL interface code, software device drivers, reference project examples for FPGA connectivity. It also contains user guides for some analog devices evaluation boards to help developers get up and running fast. At Analog Devices, we recognize that our products are just one part of a design solution. We are supporting seamless integration of ecosystems and tools by offering HDL interface code, device drivers, and reference projects example for FPGA connectivity. This community is for the discussion of these reference designs. Please visit the Engineer Zone at easy.analog.com. Analog Devices creates and maintains Linux device drivers for various ADI products. Some device drivers are also available for ADI products that connect to microcontroller platforms without an operating system. The purpose of this community here is to provide support for these drivers. To see the list of available device drivers, visit the Analog Devices Wiki. This slide illustrates the design resources covered in this session. This summarizes some of the products we covered today: the FMC-ADC ADC1 EBSET, the FMC-ADC and the FMC DAC Interposer, as well as the SDP Interposer.